Okay, so thinking ahead a little bit about the things that I think we still need to go over. There are a couple of them. One is the thing we're going to do today, which is how to organize and formalize mathematical structures, such as groups and spaces and stuff. Then I think we should have a talk about induction and recursion. That's also an important topic that deserves attention. And then there is the more engineering lecture about how to actually organize a project so that so that it's not just like some random mess on GitHub. So we'll also have that, and then the rest I think we will devote to just project work. So I think I'm going to switch some of the lectures will be replaced with one-on-one meetings discussing projects. I think that's probably going to work better. Now, as always, so I'm becoming a big fan of this Mathematics in Lean online book because I think it struck a really good balance on how to explain formalized math to mathematicians. So today we're mostly going to follow the chapters 6 and 7. We can't cover everything, there's too much in them, but there isn't so much that you shouldn't try to cover it all. So I really do recommend that you take the time and go and read these chapters, and when you read them, keep your Lean open, okay? And use the book comes with Lean code that you can then try out. Okay, so for today's lecture, we are going to discuss, first, we're going to discuss structures. And then we're going to discuss classes, or their full name, sometimes they're called type classes. From a theoretical point of view, these are all just sigma types, okay? So we're just going to talk about dependent sums. So let's remember the dependent sum. A dependent sum like this. What is this? Well, A is a type, B is a type family, so this would go into some universe. And then, naively speaking, the elements here are pairs x, y, where x is in A and y is in B of x. That's what the dependent sum is. Now, if you want to study the semantics of type theory and mathematical models of type theory and so on, then you will pay attention to dependent sums because they are important, just like existential quantifiers are important in logic, and there are good category theoretic characterizations of what the dependent sum is supposed to be. It's supposed to be a left adjoint to something, and that then gives you lots of math to study. But it's not something that you would use with your bare hands when you formalize math. Just like you wouldn't use bare set theory when you formalize math. It wouldn't work directly with sets of sets of sets of sets of sets. You want to have decent ways of working with them, even though those other decent ways are, hopefully are equivalent to the theoretical account. So the theoretical account of what we're going to discuss today is dependent sums, end of story, everybody go home, okay? But, of course, there is going to be more to this when we come to actual practical uses. When we come to practical uses, you will see, as always, that there are lots of what computer scientists call bells and whistles. So you should look up what bells and whistles are in the jargon. You should first of all be aware of the jargon. Okay, it's a Google the jargon file, and everything will become clear. Not now. Okay, anyhow. I know he'll do it anyway. Yeah. Let's go then with structures. So suppose we want to define a structure such as, maybe let's take an example. We're going to switch to the book, but just as sort of as an overall introduction, what do we mean when we talk about structures? So these would be things like a type for, say, points in the plane, or a group, or, well, now every time you say group, you can keep going and just name your favorite algebraic structures. So rings also probably, or maybe another. So there are lots and lots of mathematical structures. So in general, any kind of thing that mathematicians call mathematical structures. And now there's a lot of stuff. Apart from this algebraic stuff, maybe you will have like topological spaces or manifolds, graphs. There's going to be an unending supply of mathematical structures. And these, we want to have some sort of a system for organizing them. And this, of course, we're not the first ones to think about this, and neither are people who implemented proof assistants. So, for instance, an important influence in this direction was Bourbaki, because Bourbaki, with the books that Bourbaki published, sort of gave a very structured account of what it is that mathematical objects are, in what sense they're structures, and so on. And I think the influence is clearly visible in how mathematics is done these days. And we are going to follow essentially the same ideas. And the idea is that a structure is some stuff bundled together. That's the most naive way of saying it. So you're going to have stuff bundled together. Now, if you have to do it with sigma types, then you would say, well, I bundle together some stuff from type A, and then I'm going to add some more stuff from some type B, but this B may depend on the first one. And then I'm going to put in some more stuff. So now we'll have 3 components. And in general, each component can depend on the previous one. And so then eventually here you're going to have some other type, I don't know, T, which depends on everything you've mentioned so far. So these are going to be glorified tuples. So what will an element be? Well, an element will be like a tuple nested in some way, right? Tuples. While in principle, you might try to work with such tuples directly. That would be a bit like working with Lisp, right? I mean, you would just be like lists everywhere. So some people can do it. I can't do it. You want more structure. Also, when we refer to these components, when we have a structure, usually we want to give names to the components. Now, the names of the components as written are, this one is called first, this one is called first of second, and this one is called first of second. Okay, so you don't want to say there such things, right? You want to say the unit of multiplication, like you want to say the 0 element, or you want to say the multiplication. You don't want, when you have a group, you don't want to say the 4th component. So these are actually issues that arise not just in mathematics. For instance, it's exactly the same thing happens in computer science. If you have some data organized so that each particular datum is a tuple of things, you want to give names to the components. And so that's how we arrive at structures. Structures are also called, in programming languages, they're also called record types, because their elements are records. So The difference being that while a tuple, while an element of a nested dependent sum is some sort of a tuple, a record would be something that has named fields. So however you write them, you would say, okay, I have some field, I have labels. I would say the first field has a name and it's got such and such value, and then there's a second field and so on. So we want to name the fields. Okay, so name the components. Okay, so still thinking a little bit about what this is in terms of math, it's a bit like the difference between having, say, r to the power of the set 0, 1 and r to the power of the set where this set has two tokens called RE and IM. These are obviously isomorphic, but with this one, you would have to speak of the zeroth and the first component of an element because it would be a function that takes 0 to a real and 1 to a real. Whereas here you could speak about the real and the imaginary component, and that would be much more friendly. So that's what we want to do. So now let's look at how this is done in Lean.
Just one thing.
Yes?
Like, is there any problem here because we have this dependence on all the previous arguments in general?
Well, so the question is whether there's a problem with the dependence. So the dependence complicates things in general. It would be, you can consider the simple case where the components don't depend on each other, right? So that is the non-dependent structure, non-dependent. And the non-dependent one would be then just a Cartesian product. That's what it's going to be. Yeah. Now, of course, this is an important, simpler case, which has its role. But let us observe that for formalized mathematics, it's not going to suffice, because we are very quickly going to get examples where there is a dependence between the components. So we will need to address that. Yeah. So it's better if we just do it from the start.
But you can do this in some.
Sure, of course. You could do it, yeah. So for us, the non-dependent product is just going to be more or less a special case of the dependent one. At least that's how we're going to think about it. It's still a separate issue as to whether in Lean itself, we really want to, do we want to actually define the Cartesian product to be a special case of the dependent sum, or should those be two separate definitions? That's a software engineering question. In formalized math, I would say the larger your project, the larger proportion of everything that you do is software engineering. So if you're really good, you will manage to have to do your software engineering in a way that is not going to obstruct the math. But that is a very difficult problem to do. And I think they did a very good job in MATLib, for instance, because people don't have to learn that much to start actually using MATLib in a competent way. And also, the most important thing is when I'm formalizing some math, what proportion of time am I thinking about software engineering, and what proportion of time am I thinking about math? So that's a very relevant question. Okay, so we're now going to follow this chapter 6 on structures, not going through all of it, but let's just use it as a sort of a scaffolding by which we're going to go. And I have it here open, the corresponding Lean file. I have it here. Is this large enough, or should I make it a little bit better? Oh, how do I switch? I should switch to the light mode. I think that's generally helps.
It's like theme.
Theme.
In the command tab.
Theme.
Preferences color theme.
Okay, pick one. Light high contrast. Default high contrast light. Is there just like light without, oh, up here, I'm okay. Light Visual Studio, how about that? Light modern, oh, I'm modern. There we go. Is this better or worse? Better, okay. So nope, I want 06 structures. Where is it? Structures. Where are the structures? Structures. This is, nope. Yep, this is the one I want. Okay, so let's have a look. So when you define a structure in Lean, you have to give it a name, which is here, and then you just list the components. So here we would have a point in three-dimensional space whose components are called X, Y, and Z. Up here, we see a thing that's called a decorator. So a decorator is a notion that comes from programming languages where you have a definition, and then on top of it, you write something that you call decorator, where you explain additional things about this thing that you're defining. So in this particular case, we are instructing Lean with this X decoration that it should automatically generate an extensionality principle. So let me explain. So I think I'm going to I want to explain the math, the sort of mathy things behind this. So what's an extensionality principle? An extensionality principle is a principle of some sort, a law or a rule or something that tells you how to prove that things are equal. Okay, so an extensionality principle for A cross B, hello, would be, suppose I have two elements of the Cartesian product A cross B. An extensionality principle is going to be something that says under certain conditions U is going to be equal to V. So can you tell me what the conditions are for U and V to be equal? Well, it's going to be the first projections are equal, and the second projections are equal. And by the way, I should get you used to writing these things like this, so you should not think that this is odd. Okay, so, and the second projections are equal, then they're equal. That's an example of an extensionality principle. Okay, so another important extensionality principle would be, for instance, to say something like this. If phi is a proposition, okay, and then P and Q are proofs of phi, what does it mean that they're equal? Well, now we need to make some choices about what propositions are. But remember, at the beginning, I was like a while ago, I was explaining type theory. I said, well, you should think of propositions as types that have at most one element. So a reasonable extensionality principle for propositions would be that any two elements, any two proofs of phi are equal. So you would have something that looks like this: for all phi in prop, if you have two elements of phi, then they're equal. That would be also an extensionality principle. Another one is
this judgmental equality?
So the question is if this is judgmental equality. Okay, so first of all, anybody who doesn't know what the question meant, you can simply ignore it. But the answer is it could be either, and then people are going to speak about two kinds of extensionality principles, judgmental and propositional ones. And usually the judgmental ones are way, way stronger. And if you start throwing in judgmental propositional principles in a sort of free way, you will very quickly produce a type theory that doesn't have decidable equality checking. So you have to be careful. So people try to avoid that sort of thing, and you need to be quite careful about what you can allow. Okay, so how about an extensionality principle for functions? If I have two functions, f and g from a to b, can you tell me what the extensionality principle ought to be? Something, something, therefore f equals g. What's the something, something? For each x in a, f of x equals g of x, then they're equal. Okay, so this one is called function extensionality, and in Lean it's called funext. Okay, yeah. Every dependent sum, just like we had here an extensionality principle for the Cartesian product, this would also apply to dependent sums, right? So every dependent sum has an extensionality principle. Now, there are different kinds of type theories, but you can either adopt these principles, and as was already asked, you could adopt the stricter form or the weaker form and so on. But as far as math is concerned, you really want the extensionality principles. It's in the nature of mathematical objects that we study. We think that they satisfy these extensionality principles. This is maybe most visible with the function extensionality. A programmer might say, no, I don't believe in function extensionality because I think of f and g as source code, and then obviously you can have two different kinds of source code doing kind of the equivalent extensionally equivalent things, but it very much matters whether I use f or g, and maybe I don't want them to be completely interchangeable or something. So in computer science, you would have models where you don't want function extensionality, but practice shows that it is extremely difficult to work without function extensionality in mathematics. You just get stuck quickly. So this would definitely be something that we would like to have for doing math. Not so much for doing computer sciencey things, but for math, definitely. So in general, we would like to have nice extensionality principles. And now, if we define a structure, we expect, that we will have extensionality principles for structures just as well, because every sigma type has them, and we would like to adopt them, we would like to use them. So that's what this X business is here, because it instructs Lean to automatically look at this and generate the corresponding extensionality principle. Well, but how does it know what to generate? Well, it's just a glorified sigma. So we know what it is for sigma, compare the components. So compare the components. So now if you say check what it does is so here's the first point. When you define a structure, you get a type. This is now a type, but it is also a namespace. So it's going to stick the extensionality principle inside the namespace pointer, and it's going to call it X. And if we look at it, it's what we expect. It says point X given two implicit arguments X and Y, which are points. If you can show that the naming is a little bit unfortunate. I would prefer X and Y to be called something like A and B, but okay, we'll survive. If they agree on the first component and the second component, and the third component, then they agree. For some reason, it decided that it's going to make, let's see how smart it was. For some reason, it decided that the first and the second component are implicit arguments, but the third component is not an implicit argument. It's explicitly here, it says for all Z, for all proofs that the third, the naming is really unfortunate, okay, but it says for all proofs that that the third components equal, then it equals, then, okay. So it decided that the first and the second component, it decided that the first and the second, I'm babbling. The points themselves are implicit arguments. Then these proofs of equality are not. And then for some reason, the third one is expressed as a universal quantifier, but it looks like it could also have been expressed as an implication. So it's okay, it's equivalent. It's a bit funny why it's doing that. There's probably a good reason why it's doing that. So there could be two possible reasons. Either there is a reason for reasons of making it work better, or it's just an artifact of how the code generates these things. I don't actually know the answer. Anyhow, I have the following question. Why does it make sense to make the points implicit? Because you can tell what they are from the goal, right? So typically you will have a goal like prove that these 2 points are equal, And then if you want to use this principle, you can just say, well, use point.x, and it'll be able to figure out what the points are by looking at what it is that we're trying to prove. One is the left-hand side and the other one is the right-hand side. So it's okay. So how do we prove this? So here you have a proof that it says, okay, now we have reasonable naming schemes. If A equals B, if you have points A and B and they agree on the first, second, and third component, then they're equal. How do you use this? Well, there is a tactic which is also called ext. And so you say, if you're trying to prove an equality, you say, I want to prove it by using an extensionality principle. You say, okay, ext. And it's going to give you the three, see, you get three sub-goals. You need to prove this, you need to prove this, you need to prove this. But in each case, this is just an assumption. So now, instead of doing the three cases and writing assumption, you maybe write the first two and then you say, wait a minute, it's all going to be assumptions, okay? So you can say, oh, after that, just keep repeating assumption. And there's this repeat prime here, which is explained what it is. It means just keep doing assumption on any sub-goal, on anything that is generated, just keep doing that. This ought to work as well. This is probably the same thing. Yeah, okay, more or less. This one is a bit different. This one doesn't say keep repeating the assumption until everything's gone. This one says use the extensionality principle, and then on every sub-goal, use this particular thing. Okay, so the thing to remember is do not have three bullets and every one of them says assumption. I mean, you can, but you want to look like a noob. So, okay, how do you actually define a point? Okay, there are several ways of defining a point. So here,
extensionality principles. Are these decorators similar to like the Haskell deriving?
No, there is actually a deriving mechanism in Lean, which is very much like the deriving in Haskell. This is the decorators can do all kinds of things, and this one deriving is used to derive type classes.
Yeah,
but this is not a type class. This is not a type class. This is just like deriving a small theorem or something. Yeah. So, okay. So here, let's see, how do we actually define a point? You say, well, I want to have a point, and then you can say where, and you list the values of the fields. And so now we have a point with coordinates 2, -1, 4. You would use this if you're defining a big fat structure like a group, then you write it like this. You name the fields. If it's a small structure like this, then the triangle brackets are your friends. Careful, these are not the usual parentheses. I keep explaining this because, as I learned by myself, if you're not told that these are special triangles, you might waste a couple of hours trying to make things work. Okay, so this is the triangular parenthesis, and this one always works the following way. It says, okay, somebody gave me three things. I need to stick these three things into, and they want me to make a point. How do I use three things to make a point? Well, I will just use the constructor for the point. So there's a constructor, which is like ordered pair, or in this case, something like an ordered triple or something. And I'll just pass these things to the constructor, and hopefully nice things happen. Here is the same thing done with an explicit constructor. It's called .mc. Yes. As is usual in proof assistance, you will have default choices all over the place, like the constructor is called mc, okay? But you can also typically rename things and be more explicit. So here is another definition of a structure where the constructor is called build instead of mc. And so now you can say build instead of mc, if that's your thing. One thing to also observe is that you can then also use these as patterns. When you get to match statements and functions, you will see later that we can do that. Okay, next. How do we define functions on points? So first of all, notice that we moved ourselves into the namespace point. So what we're doing now is actually going to be point.add. So how do you define addition of functions as vectors? Well, here's one way. This is the way where we use the triangle brackets. I have 2 points, and now I want to define the third point, and I just say, well, use these three components, and the brackets will figure out what to do, because they know it has to be point.mc. That's okay. You could also write it in this long form, of course. Yes, and that will be just the same thing. And let's see. We can add points. Oh, okay, so here's maybe a good one. If I say check, add points 1 and 2, then it says, well, when you check, we'll just check the type. So it says, yep, you're going to get a point. This is not the same as eval, where you try to actually compute what you get, okay? And it says, well, yeah, I computed this thing, but I have no idea how to actually show you the result. And then we get to Yure's question, who asked, is there some way to derive classes? No. Oh, real numbers don't have, it's tricky, because how do you show real numbers? Okay, so it's not so easy to show points, as it turns out, because real numbers are not easy to display. Because if you wanted to display real numbers, what are you going to do? Compute them to how many decimals? You're going to end up wasting a lot of time computing these real numbers, when you even can. Okay.
There's one more thing.
Yes.
To like already deconstruct these points in the type declaration. So like.
So the question is, do you have to write a here, or could you just like directly decompose it? You can decompose them in functions here. Okay. Here is addition, where you say, I'm going to have a function from 2 points to a point, and then you can just directly say the first point has this form, the second point has this form, and the result has this form. Okay. So I think that addresses your question. Yes, and actually it's better than that. You can use the triangles in the parent. You see? Yeah. Like that. Okay. So what is going on now? We're now the magical triangles. The magical triangles are actually not that magical. They are kind of used in mathematical practice a lot, where when you have things, you just like say, oh, I have these three things, and you just write a tuple, and it's going to be okay. Maybe formally it's not a tuple, but people understand me. It's exactly that kind of behavior. So we see here how proof assistants are mimicking what mathematicians do. My long-term hope is that this sort of technology, which is right now just technology, see, it's not science, this is just smart tech that somebody implemented, that it's going to lead to proper mathematical treatment of things which are still at the level of folklore and culture and social conventions and stuff like that, because I think it's going to push in that direction, right? The fact that this exists is going to start pushing mathematicians in the direction of saying, oh yeah, no, this is actually also kind of mathy, and eventually it might become mathy.
And we have a way of at the same time breaking it down and having the whole thing as one.
What is the question?
In Haskell, you could also do like an @ sign either.
Oh, you're asking whether there are pattern aliases. Yeah. If you want the components and the point. So in OCaml, this would be written like this, and now you would have P and the three components. So question, do you want P and the three components, or do you want P, the three components, and a proof that P equals those three things when you put them together? And if you want the proof that they're equal, then the person sitting next to you there is going to ask which proof, because they did homotopy type theory. And then it's going to get trickier. And so if they have it, it's going to be a hack because of the questions that I just raised. It's going to be a little bit finicky. Yeah, but you cannot state judgmental equalities as hypotheses. That's the problem. And it's kind of weird to state that a given variable is judgmentally equal to something that's not a variable. Oh, okay. So one way to do this would be a let statement. You would have, say, let P equal that thing with, so that would work. But you ask good questions, but I'm not sure best answers are known yet in many of these cases, because we are just at the level of technology, which is one step away from sort of folklore and believing in night spirits, you know, it's a bit better. Okay, so we're not going to go through this in complete detail. I really urge you to read the actual chapter, but let's see what the main ideas are, because I think that's going to help reading later. So here's an important point. Apart from having just fields that introduce entities like real numbers, you can also have fields which are conditions. There's nothing wrong with having conditions, because these conditions or constraints are just propositions, and propositions are just types. And so you just say, I have an element of this type, and that's going to force the proposition, the constraint to hold. So what is this? Standard 2 simplex. What is the standard 2 simplex? Well, the standard 2 simplex, where is it? Let's draw the standard 2 simplex. So this. The standard 2 simplex is this stuff in here, right? This is the standard 2 simplex. So its points x, y such that they have to be between 0 and 1. And actually, how do you say that they're in this triangle? Let's see what they said. They said, oh, sorry, I drew a 1 simplex. Apologies, I'm off by 1. Do you know what off by 1? And now that we mentioned the jargon, right? It's an OB1 error, right? Off by 1. Okay. So yes, so there is a third component, and so this is actually a fancier picture. Oh, that's gonna be the day when we can draw pictures in Lean.
Isn't that already some
It already has plugins that allow you to visualize objects. So Jure, the other Jure Taslek, he in one of the projects we did, he put in something that shows you graphs. So it draws little graphs. So yeah.
That's why I think that it has proofs by pictures.
Yeah, proofs by pictures, commutative diagrams. You draw a diagram, then you wave your hands, and then they say, yep. Yeah. Okay.
string diagrams.
X plus y plus z has to be equal to 1. So what is this actual simplex? Let's be careful, because I drew something silly. So the actual simplex that we're talking about is you take the 3. So let's see, Professor Laurich taught us that it has to be like this. Okay. And so then it's this triangle. It's actually an equilateral triangle. It's here. It's this triangle, right? Its coordinates where x plus y plus z equals 1. So that's some sort of a plane, but then you take just the first quadrant. Okay. So it's this triangle, and you write it like this. You say the components have to be positive, and then you put in the requirements. Yep. So now if you want to make an actual simplex,
X.
okay, it says x, y, and z are missing, so I can say x equals, I don't know, let me try my luck, 1/3. I'm very much afraid of the real numbers. Y is, okay, let's go easy, okay? Z equals 1/3. Yep. So it still wants stuff. Now it's becoming a little bit annoying that I have to do this by hand. So maybe it would be nice to have a way of saying up here in the structure that certain fields maybe have default values, or that certain fields can be derived using such and such tactics. And of course, these things exist in Lean. By what? Any idea? Simp? Sure. No goals? Well, no. Where is, yeah, it still wants things. Yeah. Why non-neg by simp? So as you see, this tool is not really made for people to actually make simplices. It's for people who want to think about simplices without making them, right? And now it wants what? It wants to know that 1/3 plus 1/3 plus 1. Okay, I'll just like simp is your friend. Nope. Ring. Ah, there we go. Okay. Let's keep the stuff here. Here's the next important step. When you define a structure, it is allowed to depend on something. So what is this in terms of dependent sums? In terms of dependent sums, this is saying, if if this is points in space, this is a point in space, right? So if I want, or a simplex was this and some conditions. So now if you want an n simplex, it's really a type family, right? So it goes from natural numbers to type. And for each natural number n, it has to give you a specific type, and that specific type is some sort of a structure, blah, 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 but it may depend on n. So we're now not defining a simple type, just a type. It's not a fixed type, it's a type family. It takes natural numbers to types. So what does it say? Given a natural number n, what is a standard simplex? You've got V for vertices, which is a map from fin n. Fin n, what is fin n? So let's learn that if you control click on things, you can say go to definition, go to declaration. You can also just hover and it's going to tell you what it is. Fin is a natural number. Fin n is a natural number I with the constraint that 0 is less than 1 is less than n. So this is the canonical type with n elements. And amazingly, this is how we define the canonical types of size n in logic and sets in the first year, those of you who were there. Right. So there's some agreement between mathematicians. And now you have to do stuff like write more complicated conditions, but still the point here is, yep, it may depend on things, and we're going to use this a lot. Okay, you can also define structures that don't actually have any data, they only have conditions. And this is also quite useful. So you can say, for instance, what does it mean for f to be linear? Well, you can say it like this. It has to satisfy two conditions. One is that is additive, and then what does that mean? And one is preserves. So in Slovenia we say homogeneous, and here it says preserve mol. Okay, sure, but they didn't say preserve add, so I don't know. So these are the two conditions. Now this style is the style that mimics what you will see in a classroom on linear algebra, or in a book on linear algebra. That's how it's going to be defined. It's going to be defined as a function f is linear if it satisfies these two conditions, and the conditions will be named because we need names for them so that later on we can discuss these conditions. First order logic is here. This is the same condition written in first order logic. If your teacher in linear algebra walked up to the blackboard and said, f is linear when, and then wrote down this formula, right? This would not be so good. It's difficult to talk about it. It's kind of annoying. You have to remember that there are two conditions, and that the first one is the one about addition and the second one is about multiplication. Whereas up here, it wouldn't matter if I reversed the order of the fields because they have names and they do not depend on each other, so I may do so. So, okay, this is a case where you see how type theory is closer to practice. And in fact, you will see that most formalization will use this form, not the other form, unless, of course, you're in a proof assistant that is sort of based on first order logic, and then you do everything with first order logic. But Lean is not like that. The same goes for, say, simplices. We define the standard simplex using conditions, but we could define the standard simplex this way, and this would be less unusual, right? You would actually see this defined in a math class. You would see this defined like this. How would you define the standard simplex? You would say, well, it's those points in R cubed. such that, this is such that, and then the conditions would actually be spelled out as a formula, and you would not name the conditions, right? Usually you would not name the conditions. So one wonders if there is a third variant.
Just one thing. What do the curly brackets mean? Like right of
this one?
Yeah.
This is a subtype.
Ah, okay.
The type of all natural numbers such that n times n equals n. What? Oh, sorry. I want an example. I want an example of a type. And here's an example of a type. The thing I wrote earlier is not finished. I want an example which is an element of this set. Well, okay, let's give it. It's got two components, a number and a proof. But it doesn't know how to synthesize 1 times 1. Okay, so maybe by ring. Okay. Okay. So that's sort of like a little bit of basics about structures. You can have structures and, oh, maybe let us look at what happens at the next level, because we just went through this sort of funny small case of points. You are actually, this is an example. We're going to have a short break. Let's just have a look. This is how you would define a group. Okay. Now, there are a couple of important things here. So first of all, no, let's have a break and we'll discuss this definition of a group later, because there are things to be said. Okay. So break 15 minutes.
Well, this group is an example of some.
Okay, so we said we are going to discuss this next definition because it's, while formally it's still just a structure, is very different in spirit. When you define a structure describing points in the space, that's, you know, in terms of math, it's a small set. But when you define what a group is, that's a different story. Now, let us read the definition first. This is the definition of a, properly speaking, of a group structure on a set, on carrier alpha. So the carrier is the is a parameter. It's not part of the structure proper. It's a parameter. So this I would call group structure on alpha. And then it says that we have multiplication. We have an element called 1. We have an inverse operation. And then we have the familiar group axioms. Let's be a little bit careful. You will notice that we only have one inverse. We only says that inverses are left inverses. Does it follow that inverses are also right inverses? Because it seems like we're missing that. Yes, actually, yes. Okay. So this is a design question. Should we have both axioms, even if they're not, you know, if should the fields be kind of independent, or should be repeating them, or what should you be doing?
It's something like in Haskell where you kind of state automatically
Yeah.
one conditions.
Right. So Haskell would allow you to have another field, which is cancellation of inverses on the other side, where this is flipped around. But then it would also tell you how to get that field from the others, how to build it. Yes, you can have that. Yes.
How do we decide what is a parameter and what is a field?
So this is precisely why I'm stopping at this definition, because the question is super important. How do you decide what is a parameter and what is a field? Before we form any opinions, let me tell you what the math background of this is. Okay. So in mathematics, so this is something that is good to know in general, which is display maps versus fibrations. And you could see how Mabel raised her head because I started saying things that would attract her attention. This is more general than homotopy, but it's particularly important in homotopy. Okay, so we can start by observing that the category, the slice of set over A is equivalent to set to the A. What does this mean? Elements of this category are families of sets indexed by A. So an element here would be a map from A to the universe of sets. Whereas elements here are maps into A like this. Okay, for the purposes of this, I'll leave to you the question of what happens with morphisms. Let us observe objects only for this discussion. So how does this equivalence work? If I give you a map like that, let's call it F, how do you get let's do it like this. So the equivalence, it takes a map and now it needs to produce a family. So I need a family which is going to take a little a in A and produce a set. How do I get a set out of this? I have a map F, I have a point in A. Where will I get my set? I take the fiber. Okay, so I take F star, to be quite precise, F star singleton A, but let me also write it like this and explain that this means those C's in C such that F of C equals A, the fiber at A. And people might write this also as C sub A, depending on where they came from. Okay. Now, that's one direction. What's the other direction? Given a family B from A to set, how do I get a map into A? Well, I form the dependent sum. And then I project down with the first projection into A, and I have a map. You can think for yourself that this forms an equivalence. If I start with a map F, then I take the family of its fibers, then I sum up the fibers, I'll get back the same set. We can even draw pictures of how you have like a salami, you have a sausage, and then you cut it up, and then you glue the pieces back together, and you have the original salami. Maybe. No? You lost? Okay, let's draw the sausage. So if I... Oh, you were lost before the sausage. Maybe the sausage will now explain things. Let's try. So here is the sausage, and here is sort of a line segment, and we can sort of map down. What is, if I take a point here, then the fiber is everything that maps to this A is one of these slices. Right? So this would be this is the slice at A. So what we can do is we can now form the family of all these slices. So you cut up your sausage, you neatly arrange this on a plate, nobody ate anything, you put it back together, and you have the original sausage. Okay, it's kind of funny, right? Because you know that you're not going to have the original sausage, which is actually an important mathematical point. Because when you take some slices and you just sort of arrange them together, you're not gluing them in any way. So there is some question about properly gluing the thing, which leads to all sorts of interesting ideas. However, this is not what we're discussing right now. What we're discussing right now is, what does this have to do with groups and the question of how do you decide which things are parameters and which things are fields? The question was, how do you choose this as the parameter and these things as fields? Because after all, I could just do the following. I could say, hey, I can have weird group where this is actually up here. I can take any one of these fields and put it up here as a parameter, and it's fine. See, it works. So now I have a structure of a group, but now this is now, what is this? This is parameterized by a carrier and the operations, and all that is left are the axioms. So how should we do this? There seems to be a lot of options. Okay. Now, let me first explain what this has to do with display maps and fibrations. The display map case, this one, let's now draw the groups. Okay. So if I say that my group here is indexed by alpha, that's going to look like this. It's going to say, oh, group is something that goes from type at some level u to type at some level u plus 1. Namely, it takes alpha to the relevant structure, which has mul and add and blah, 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 blah. Actually, it's not type u plus 1, is it? It's still the same type. Okay, so you see how they used stars here? Because they don't want to think about what happens? Okay, excellent. Good idea. Let me just ignore the indices. You can think of them later. Okay, some indices on type universes. But the point is that now my space, the space that used to be A, this space A here, is now some type universe. And then I land in some other type universe. So this is what we see in Lean. But the other option would be to say, oh, I can actually have a structure, and now this structure would actually have a carrier, alpha, which is in type star, and then it would have mul, blah, blah, blah. No, not int, it was 1 in all the other fields. So now 1 in all the other fields. Okay. So these are our two options. We can stick something in as a field or we can have it as a parameter. These are precisely, this is precisely family versus display map. Where is the display map? I don't see a display map. Well, there are lots of fields here. So you want to be a little bit specific about which field we are discussing. Which one are you thinking of projecting? I'm thinking of projecting the field alpha, the first one. Because in principle, there could be many. And so then you don't know like which one you're talking about. Well, we're talking about the first one. And that generates the display map versus this family. And now we also know how to go from one to the other. At least we know how to go from the parameterized one, from the family view to the display map view. Now, from an engineering point of view, what are the advantages? This sounds, because these are equivalent ways of doing things, your first mathematical instinct is going to be, doesn't matter. But then your programming instinct will say, oh, stop, wait a minute. Of course it matters. If it didn't matter, we would just be programming things in assembler, because it doesn't matter. They're all Turing equivalent. So we would want to think carefully what this is going to do to software development. Which one is better? There are a couple of decades of papers worth discussing this in various ways. People trying to figure out what to do. I don't think that there is a unique best answer. You are in a space of equivalent possibilities, and in some cases, some of them work better than others. But through practice, it has been established that it is generally the way, at least the way proof assistants are designed these days, you will probably slightly prefer the fibered point of view, not the display point of view. You can also ask, is there software that uses the display point of view and does it well? And the answer is yes. If you look at the proof assistant called Arend, it's designed in a way that makes this one easy, but Lean does not make this one easy. Okay. Arend was designed by JetBrains, by the way. So why does it make, what are the advantages? Okay, so here are the advantages. What is the advantage of having everything in a single structure? You don't have to decide what the parameters are. You don't have to decide which things are the parameters, because parameters, alpha is distinguished here. It's special. See? In this definition, alpha is special. In this definition, alpha, mal, 1, and inv are special because they are parameters. So that's they're somehow sticking out. So the advantage of this one is you don't have to decide what is special. You just say what your object is. Huh?
Could we have like everything inside of the structure? Because I mean, just thinking from a purely practical mathematical point of view, you think of a group as a sort of a tuple of elements.
Yes. So at first sight, it's, yeah, I agree with you. At first sight, as a mathematician, you're going to say, no. This is what a group is. A group is a carrier set together with something. Right? But you will secretly, very often. So what is the next? By the way, in the next step, you are going to say, oh yes, I know that a group is a tuple, but I'll just refer to it by its carrier.
Exactly.
Okay? Now you have to be very suspicious of this. So on the one hand, the mathematician is telling you the holy truth is that a group is a 4-tuple and that the first component is called the carrier and it's a set and it's not special. But then in the next sentence they say it's special because I will refer to the entire group just by mentioning the carrier.
It's because they have a canonical structure in mind.
Right. So let's analyze. What is the mathematician doing? How can they possibly get away with this? Because it's not formally correct. And it's exactly what you say. When they refer to just the carrier set, they're relying on the fact that everybody will know what the group structure is supposed to be by mentioning just the carrier set. If I say the integers, there is essentially one way that you can think of the integers as a group. And if you're not thinking of that way, so there's something wrong with you. You're a social weirdo, right? So there's going to be social pressure for this kind of uniformity because it enables communication. That's the important thing. Okay, so while mathematically this is the natural one, where you bundle everything together, the mathematical practice shows that that's not how we do things. We really do refer to pieces of structure, and then it is implied or known what the rest of the structure is. And this is what we are going to try to capture, which also gives us an answer to what we should be doing to answer Noah's question, how do you know which things are the parameters? Well, the parameters are the things that are special when you speak about these things. Because the carrier of a group is special in your mode of speech, that's why it should be the parameter. So I come back to my previous point. I hope that one of these days this is going to become math. It's not math. I'm mentioning speech. I'm mentioning communication. That's a problem for mathematics. At least I think it should be. Okay. Now, what are some? Okay, so nobody ever says, consider the set such and such equipped with these three functions. Oh, everybody knows this is a group, right? You never say that, so we're never going to use this one.
And just one more thing.
Yes.
When you talk about algebraic structures categorically,
Yes.
I guess the fibers approach is better in that case as well.
Well, it depends on what you want. So, if you want to define the category of groups,
No, I mean, like,
the objects will be the bundle groups. Isn't that the case?
yes.
Right? You
Yeah.
will say the objects
No,
are
I
the
mean,
bundle.
like algebraic structures internal to internal to you say like
Oh, internal to something. Okay.
Some category.
Uh,
You're essentially taking the objects as fibers.
yeah. So it depends on how you want to speak about things, but often the more logical the form of your formalism, the more it will want to look like vibrations. Display maps is something that is enjoyed by category theoretic people because once you have display maps, you're really quickly going to have lots of commutative diagrams. Whereas when you have vibrations, it'll be easier to write down formulas and stuff. Yeah. Okay, so there's one important case where we really want groups to be bundled as sums, which is when we think of a group as an element of the category of groups, which explains this naming convention here, which is used in MATLib. You make a structure on a carrier set, and then you say cat, and you bundle together. Yeah, and you will see a lot of this. And there are mechanisms, there's support for doing this in a nice way.
What does this do for the morphisms?
So let's see what happened here, by the way. This is now passing. So what is this? This is going in the other direction. This is defining the display view of groups. So a group as a non-fibered thing has a field called alpha, and now instead of copying all these fields down here, they just said there is one other field called str, for not for string but for structure, which is the structure group on alpha. So again, up to isomorphism, we didn't really do anything. This is just reassociating the sums, so that now it's sums ordered they're reassociated. The dependent sums that are under this are just reassociated, but this would be the display map point of view. Right? You will need both. As you see, you need both. Yes?
So when we speak of the categories, when we don't have the morphisms.
We don't have the, this defines the objects. We don't have the morphisms yet.
Okay.
Yeah.
Of
course.
That's the one category.
But this would be the type of object of the category of groups. It would look like this.
That's what the one is for.
The one is there because these are lecture notes, and there's already a thing called group in MATLib, and they need a name that isn't clashing. Yeah, this is just to avoid name clashes. Okay, let's see. How is this called? A group. Oh, okay. It's fancier than that. Yeah. Protected means that even if you I'm speaking off the top of my head, but I think it means the following. Even if you open the namespace group, you will still have to refer to this thing as group.invmul_cancel, because there's some other invmul_cancel somewhere, which is like infinitely more useful. No, please don't. No, it's gonna start recompiling MATLib. I'm sorry, I apologize. Okay. Let's hope it's not doing that.
Just one is since this is also similar to Haskell in the sense of it's defined as a type class where it extends on.
Second.
So if you look at the definition of the group in
Yes.
MATLib.
Yeah, it's a class.
It's saying, and it's extending another class. So when you define a group, can you in MATLib define it by listing everything in one list, or do you have to say first G is a development monoid and then
No. This is a design decision in MAT-FORMATH to do it in this hierarchical way.
Yeah, but when you're actually defining a group, you can list all of them.
You can if you want to.
Okay.
Okay, so there are now at least some other questions that we need to address. So the questions that we need to address are related to how we are going now. We discussed so far how to define a single structure, and we already saw that there are a lot of interesting questions about what is a parameter, blah, blah, blah. But it's worse than that. These structures don't exist in vacuum. There are many of them, and they're related. So, for instance, how would you define a ring? Well, when you define a ring, you would want to say, aha, but a ring is an abelian group, right? So a ring has two operations, and the 0 and the plus will make it into an abelian group, whereas the 1 and the dot, let's say these are unital rings, the 1 and the dot will turn it into a monoid. And the abelian group, in fact, is a monoid of a special kind. So we are starting to see some sort of a hierarchy of structures coming up. So now the question will be, how do we do this? So there's a question of how to organize. Hierarchy is one of those words here, where if I stop to think how to spell it, I can't spell it. And there was another question that we already touched upon, which is also important, where we said, oh, but people refer to a carrier set and they think everybody knows what the implied group structure is supposed to be. So there is a question of how to know the implied missing structure. How are we going to do this thing in a proof assistant where I say integers and then I say the inverse of 7? I say 7 is an integer, consider the inverse of 7. You know what it is, right? Why do you know what it is? Well, you know this because you know that the integers form a group. But how do you know the integers form a group? So how is Lean going to do this? So there's something that needs to be addressed there. There has to be a mechanism.
Do you mean that Lean is supposed to infer the whole structure? Or because I thought we to define it and make it canonical.
Okay, so let's see. So let's analyze the situation with the integers. Why do both of us agree on the structure, the group structure of the integers? It's because we were told about it at some point in time, and it's in our brains, and it's the one that we use, right? There is some slight danger that we would be told about two structures on integers that are both abelian group and they're equally important and used all the time. And then we wouldn't know which one is meant. But this situation does not arise in practice. If that were the case, we would have two different names for these things. We would not call them like the group structure on the integers and then confuse ourselves all the time. So keep in mind, right? So we only need to solve the problem of how. So the reason why we agree is because at some prior time we agreed.
Yes.
We were explicitly told that this is the case. So what we need is a mechanism that will tell Lean what these conventions are.
Yes.
Right. However, you had a question about inference, right?
Yes.
So, right.
This, what I so I'm more used to Coq, but what
Yes.
I used to do in Coq is either defining a structure and telling Coq that this is a canonical structure on this carrier, or having tactics that will generate the canonical structure, and I have to prove that the tactics indeed.
Okay. So what you're mentioning is that there's sort of a basic case, which would be something like the group structure on Z. But then there is also the far more interesting case of inferring the structure. This one would go somewhat like this. Suppose we know that A and B are groups. Okay? Then A cross B is the carrier of a group. Well, first of all, notice how I already misspoke up here and nobody yelled at me. It's not that I really meant to say that A and B are groups. I meant to say A and B are sets which carry some unspoken group structures. That's what I really said when I said, suppose A and B are groups, okay? And then I say, well, then also A cross B carries a group structure. And everybody knows what it is. So we also need to cover this case. Both of these cases are covered by a mechanism that is called type classes or just classes. I think it's okay in the context of Lean to just drop the type and also talk just about classes. But in Haskell, for instance, I think they're going to yell at you if you have to say type classes. Otherwise, you're like, what is going on? Okay. Yes. Okay. So let's now compare these two questions. One is how to organize hierarchies. This one is in effect, this one is kind of easier to do, which is, well, if you observe what is going on here, you will see that essentially what happens is that you have a structure and then you extend it with more structure, or some structure contains smaller structures. So we need a way of extending structures so that you don't have to keep repeating these fields. And that's what the extend thing does. So if you look at I want to find it here somewhere. No, not here. Search here. Extend. Nope, not yet. Then it's going to be here. Here, when you say extend for a structure, this is for a class, but you can say it for a structure just as well. It just means it's going to add more. It's going to extend this one with a field. So we can actually try an example. Let's see, do we have the time? Yeah. Okay, so my goal here is to explain the reasons and the reasoning for why these structures and classes exist. But how they actually operate on a technical level is explained very nicely in the notes that I'm referring you to. And it would take a long time to go through everything. But let's try some things because, you know, we want to have some concreteness here. So for instance, here we define the group, okay? So let me say structure cow alpha type star extends group, or actually maybe not. Well, yeah, sure. Extends a group. Suppose I have a group on alpha, then I can extend it by something else. So X and X. It's not such a super strange axiom. In fact, these groups have some mathematical relevance. It's when every element is an inverse to itself, is essentially what this is saying. So what happens if I say, what does cow look like? Okay, no. Yeah, so here are the fields. This is what I wanted to see. So let me make this bigger. So if I say, what is this structure? It says it's got a field called toGroup1. So what it does is it includes the group 1 thing as a special field called toGroup1, and in general it's going to be called to whatever it is. And then you can access the group structure by accessing this field. And then the other one is the axiom that I wrote. Yep. We immediately see that a couple of points. We will not want to actually explicitly access to group 1. We will want this sort of inclusion of fields to be automatic. So for now, for instance, if I say now that cow has multiplication, this is false. Cow does not have multiplication. Cow has a field called toGroup1, and that one has a field called multiplication. So whenever I want to multiply something that is in a cow, I have to say dot toGroup1 dot mul. I very much don't want to do that. So I will want something. What is the something? Well, the something is called a coercion. What is a coercion? A coercion is a map that is applied automatically as needed to make types work. Instances abound. 7 is an integer. 7 is a real. Well, which is it? So one way to deal with the fact that 7 is both an integer and a real is to say primarily 7 is an integer. But if I ever mention 7 in a context where a real is needed, then I will insert a canonical coercion from integers to reals because there is one that is reasonable. By the way, this is not how 7 is interpreted in MATLib, because 7 could also be an element of any ring because it's 1 plus 1 plus 1 plus 1 7 times. So it's more complicated than that when it comes to 7, but you get the point. So this question of how to organize hierarchies, the short answer is we will allow structures to be extended. Yes, and now there are technical details after that, but I want to explain the overall ideas. We allow structures to be extended. Yes?
How do you do when you want to extend two different structures? Like
here, when you, so are you asking about the diamond problem? Or yes. So when we extend structures, let's have a look. I think the ring already gives you the diamond problem. So, okay. So let's be a little bit careful how we're going to do this. Okay, so a ring structure on alpha, yes, is an abelian group structure on alpha and a monoid structure on alpha. So what happens? So this thing is going to give me 0, plus, and minus. This thing is going to give me a 1 and a multiply. But, of course, somebody at some point decided the abelian group is actually just a monoid. So it looks like I have two copies of the monoid. So wait, no, we don't have a diamond problem here. Do we have it? Not yet. The diamond problem appears when the following happens. You have your structure, which is the extension of two different structures, but these are both the extension of a fourth structure. And now the question is, do they share the fourth structure or do they not share the fourth structure?
It's not happened here.
So it's like I want two copies of monoid. You have it. Well, you will have it because, oh, sorry, because I said abelian. I'm saved by the abelian. What is abelian? Abelian means, so let's go on. I will not actually get this here. Here I will say, oh no, but abelian group, that's like a group which is also abelian. So there's going to be an axiom here that it's abelian. There will be axioms of distributivity here. There will be axioms of a monoid here. And this group is a monoid. right? Yes, they're always all on alpha. So do we have two monoids or one? Do we have two monoid structures or one? Two. So we don't want this. We want this. But sometimes we want that. That's called the diamond problem. This happens also in, say, object-oriented languages, where you have a kind of a similar problem of whether you need two copies of something or one copy of something, and then some programming languages use one default solution, the others use another default solutions. There are languages that allow you to specify what is going on. So the notes will explain what goes on here. So the class mechanism works slightly differently, I think, from the structure mechanism in this case. What is the class mechanism? The class mechanism is let me spend the last 4 minutes explaining the idea of the class mechanism. We often face the general question of reconstruct missing info. And so far, we have seen that implicit arguments are one such mechanism. That was the last time we said, oh, you don't have to specify all the arguments. They may be missing, but Lean will figure out what they are. And if it doesn't, then it'll complain. This was used when you can precisely tell what's missing by just looking around and say, oh, I can figure out what's missing. It's this one particular thing. It's forced on me. There is no question that that's what's missing. But now we have a different kind of missing info, which is what is the implied structure on the integers? That's not something that you can derive from mathematical facts. You need to be told about it. And so the structure, the class mechanism is what that does. And it's actually kind of a simple idea if you think about it. So the class mechanism is this. Just like with implicit arguments, we used curly braces to say, this is an implicit argument. I'm not going to tell you what it is. You need to figure it out. With the class mechanism, we use bracket arguments. And when you see a bracket argument, that means I'm not going to tell you what it is. Lean, you have to figure it out. But Lean says, okay, but this is now something like a missing structure. I can't just dream one up. You have to tell me the rules, the social rules of reconstruction. So there needs to be, so this is forced info. Forced on what gets reconstructed. This needs to be, you need to have rules on how to reconstruct. These rules are called type classes. And they are also structures because we use this to reconstruct missing structures. So whenever you define a class, it's also a structure, but more importantly, it tells Lean that that's one of the social rules that it can use to reconstruct. Okay, I'm calling them social rules because I'm being mischievous here, but it's a given rule. It's something that the user specified. This is not mathematically forced. The user can make really bad decisions. And so if they provide two group structures on integers, Lean will find one of them, or maybe the other one, and in some situations one, and in some situations the other one, and that's going to lead to large amounts of chaos down the road somewhere. So you need to be kind of careful what these rules of reconstructions are that you give to Lean. You should avoid, whenever possible, any kind of ambiguity on how to do things. It's not polite to teach students two ways of defining a topology on a space and then say they're equivalent, they're equal. You are going to guess which one it is. Well, we do that to students, but Lean is not going to take it, right? So Lean is going to get It's going to use one of them, and then you maybe think it used the other one, and then you're in for a surprise. So whatever the rules of reconstruction are, we should strive to make them unique. It may not be always possible to do, but we should strive to make them unique, because that sounds like a better idea, because the same mechanism in human mathematics is mostly unique. Of course, it's not exactly unique, but it's mostly unique. So with this, I think I invite you to read about the classes. We didn't get too much. Unfortunately, we chatted so much that we didn't actually look at what this is doing, and it's now past. So for instance, here's a class that says, I have a type, it's got an element called 1. This is how you would start defining a monoid, maybe. You say, first, there were things that had an element called 1. And then you would give rules of how 1 is generated. And then you would say, oh, there's also a class of things that have a binary operation, which is called dia. It's called dia because we want to use a very small unreadable diamond sign, which is not a dot, it's a diamond sign. To get the diamond sign, you hover, and it will tell you that you have to write diamond to get the diamond sign. So, okay, I'll blame this on my font. Yes. So it's an operation called diamond because they did not want to commit to dot or plus, so they said diamond. And then there is a thing called semigroup, which extends to diamond. Yes. And then blah, blah, blah. And so it's starting to give lots of rules. So this one just says, so let me maybe point this out. When you have, when you say this did not actually give any rules. This just said it is possible to give rules about a set having an object called 1. But I didn't give any rules. But I could. I could say, for instance, the integers or the natural numbers have an element, and I'm not insane, so I'm going to call this element 1. So now if I'm supposed to give a natural number, okay, I can say 1. No, okay, why does it not work? Oh, because it's in the namespace 1. There we go. There's a namespace problem here, which would have to be fixed. But I can say, which natural number are you thinking of? I'm thinking of 1. And then what will Lean do? It'll say 1, 1. What is 1? Oh, 1 is an element of such a class. Wait a minute. I need a class 1, 1, 1 on NAT. Do I have a class 1 NAT? Yes, it's called cow. It's here. So this is saying there is a social rule of naming things 1. This is an actual instruction that whenever you want an element called 1 in the type natural numbers, you should use this one here. And if I give you 2 of these, then you're asking for trouble.
If you do eval here instead of example, would it actually print it out?
We got number 3. Okay, don't do this. Okay, we're done. So read chapter 6 and 7 because they will tell you how this works operationally at the level of mathematics.